Hello and welcome. So in this tutorial, we are going to learn some tools for homotopy computations in simplicial complexes from graphs. So given a finite simple graph G, there are several methods to obtain a simplicial complex from G. The most common examples are like clique complexes, independence complexes, and matching complexes. So the clique complex of a graph G is a simplicial complex whose simplices are cliques in G. The independence complex is a simplicial complex whose simplices are independent sets in G. And similarly, the matching complex is a simplicial complex whose simplices are matching in G. So these are three different types of simplicial complexes coming from a graph G. And we can realize this as a geometric object. So one can study their topology, one can compute their homotopy type. But the fun fact is that we don't need different type of tools for this different type of simplicial complex to compute their homotopy type. This is because the matching complex of a graph G is the same as the independence complex of the line graph of G. And the clique complex of a graph G is the independence complex of the complement of the graph G. So if we have sufficient tools or for the computations purpose for homotopy type of independence complex of a graph G, then we can compute the homotopy type of the clique complexes as well as matching complexes also. So before going to the tools and techniques, we have these two terminologies, the open neighborhood of a vertex and the closed neighborhood of a vertex. So given a graph G and a vertex U in vertex set of G, the open neighborhood of U is defined as the collection of all the vertices V such that V is adjacent to U, and we denote it by N open bracket U. The closed neighborhood of a vertex U in the graph G is defined as the singleton set U union the open neighborhood of U, and we denote it by N close bracket U. So the main idea to determine the homotopy type of a independence complex of a graph G is to apply some tools or develop some tools and techniques to the graph G and obtain a new graph with less number of vertices or less number of edges. And by repeating the process with the given tools and techniques, one can determine the homotopy type of the independence complex of a given graph G. So the first technique is domination technique. So suppose we have a graph G and we have two distinct vertices U and V with the open neighborhood of U contained in open neighborhood of V. Then there is a homotopy equivalence between the independence complex of G with the independence complex of G minus V. In this case, we say that V is dominated by U because all the simplices which contains V can be joined with U and forms a simplex in independence complex G. So for this situation, we have an example where we have this graph, which is a grid graph, and we can see that the adjacent vertices of this purple color vertex U, which are green vertices, are also number of this orange color vertex V. So we can remove V from this graph and we can obtain a new graph with less number of vertices. And by keeping the homotopy type same of the independence complex of both the graphs. And now one can proceed with this newly obtained graph with less number of vertices. Another technique is called local domination technique. Suppose we have a graph G and A is a vertex in G. Suppose there exists an independent set LA such that for every independent set sigma containing A, there exists B such that satisfying B union sigma is an independent set. So in this situation, we say that A is locally dominated by this independent set LA, or in terms of simplicial complexes, for suppose in terms of independence complex of G, we say that A is locally dominated by this simplex LA. Then again, we can remove the vertex A from the graph G and we can preserve the homotopy type of both the graphs, the independence complex of both the graphs. So for this situation, we have this example. So suppose we have this graph G where we can see that the maximal independent sets containing A, the purple color vertex A, are A, C, F, and A, D, F. So we can observe that both the maximal independent sets contains D and F, which also forms an independent set. So this gives you an idea to choose LA. So we choose here LA as D and F, which forms an independent sets. And we find that A is locally dominated by LA. So therefore, the independence complex, so therefore we can remove this vertex A from this graph and we can obtain a new graph with less number of vertices by keeping the homotopy type of independence complexes same. The other technique was developed by Adamczyk. So suppose we have a graph G and V is a vertex in G. If independence complex of G minus close neighborhood of V is contractible, then independence complex of G minus V is homotopy equivalent with independence complex of G. So again, we can remove the a vertex from the graph G and we can keep the homotopy type same. So for this situation, we have these two examples where in this grid graph, we can see that if we remove all the adjacent vertices of this orange color vertex V, then we will obtain a disconnected graph with a singleton vertex U. So which says that the independence complex of G minus close neighborhood of V will be a simplicial complex with a cone vertex U. And since there is a cone vertex, cone, so it means that this simple independence complex will be contractible. And it suggests that to apply the previous technique that we discussed, and we can remove the orange color vertex from this grid graph, and we can obtain a new graph with less number of vertices by keeping the homotopy type same. And again, in this example, this graph, we can see that if we remove all the adjacent vertices of this vertex A, then we will have an disconnected graph with a singleton vertex F, which is again going to give a contractible simplicial complex as independence complex of G minus close neighborhood of A. So again, we can apply the earlier technique and we can remove this vertex A from this graph and we can obtain a new graph with less number of vertices. And we can proceed further with this graph. The next technique is called simplicial vertex technique. So suppose we have a graph G and V is a simplicial vertex of G. That is, all neighbors of V are pairwise adjacent, or you can say that all the neighbors of V forms a clique in G. So suppose the open neighborhood of V contains contains vertices W1, W2, W3 up to WK for some K. Then we have this splitting where the independence complex of G is homotopy equivalent to the wedge of I equal to 1 to K, the suspension of independence complex of G minus close neighborhood of WI. We have an example for this technique as well. So we have this graph G and we can see that the neighbors of this vertex V forms a clique W1, W2 and W3. So we can now we can remove the neighbor. We can just obtain three different graphs, the graph G minus close neighborhood of W1, G minus close neighborhood of W2, and graph G minus close neighborhood of W3 by removing first all the adjacent vertices of W1, then all the adjacent vertices of W2, and then all the adjacent vertices of W3. And we can represent the independence complex of this graph in terms of the independence complexes of three different graphs with less number of vertices. And now we can proceed further with using the above tools that we have discussed. So these are some tools to compute the homotopy type of independence complexes of a given graph G. I hope you enjoyed this tutorial. Thank you so much.